my name is Julia and I'm a student reporter at the Hybrid Nanomaterials Laboratory, and I'm standing inside the lab right now as two researchers are uncovering a major flaw in how we measure the materials inside solar panels. Specifically, we are talking about perovskites, which are the materials used inside next generation solar panels and solar cells. But recent work may suggest that there is a flaw in the way that we measure these materials. And to get the inside scoop on this, I'm going to be speaking to one of our undergraduate researchers, Daniel Zhang. Daniel, do you want to tell us a little bit about what you've been doing this summer?
Sure. I've been studying space charge limited current, or SCLC, in metal-halide perovskites. These materials are super promising for clean energy devices and photovoltaics. But there is a major issue, as we said, in how researchers extract key parameters, especially charge mobility and trap density.
Wait, so what's the issue?
So these materials carry mobile ions, in my case Br- from cesium lead bromide, synthesized by Professor Ado's lab with this physical vapor deposition chamber. So we put it on these oscilla S161 substrates, and when we make them, it turns like this. So traditional SCLC measurements depend on single carrier devices, electron only or hole only, but that's not true for most cases. These ions drastically alter the results, the shape and magnitude of our IV characteristic curves. So to model this, I used pulse voltage measurements to separate the fast electronic response from the slow ionic one. I tracked the current voltage characteristics over time, and it turns out when you extract these current values, it actually makes a huge difference.
So could that mean that people have been calculating the wrong mean values?
Exactly. So we use something called the Mach-Gurney law to calculate these values, and this law assumes that the current follows a square law dependence with voltage. If ionic effects change the current voltage characteristics over time, you're mischaracterizing mobility and trap characteristics.
I used Python codes to map this out and show that standard assumptions just don't hold up. The field needs updated, reproducible methods for these type of materials, and I intend to set a benchmark with the SCLC community to measure mixed electronic ionic materials.
One is the loneliest number that you'll ever do.